Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. We are looking at a series of lectures in computer networks. Today we will be looking at some digital transmission technologies. As part of digital transmission technologies, we will look at one of the trends that has evolved of late, which is the asynchronous transfer mode. So today's topic as such would be basics of BISDN, and then we will look at some basics of the asynchronous transfer mode, which is ATM. So let us first take a look at an overview of what we mean by broadband ISDN. We have already looked at narrowband ISDN in a previous lecture. So we are looking at what we mean by broadband ISDN. ISDN, as we know, stands for Integrated Services Digital Network, and when we say BISDN, it essentially means Broadband Integrated Services Digital Network. It has been designed to provide services which are similar to that of ISDN, and it is substantially more capable than ISDN. So, if you look at the technology behind ISDN, typically it uses the asynchronous transfer mode technology, that is ATM, for doing the switching, and for transport, that is at the physical layer, typically it runs on synchronous optical network or SONET based networks. So, if you just do a quick comparison of BISDN and ISDN, or BISDN and narrowband ISDN, or NISDN as we can call it. So, NISDN uses existing telephone network, typically using copper pair, whereas BISDN uses optical fiber. So, that is at the physical layer you have this difference, and NISDN is primarily circuit switched, whereas BISDN uses only packet switching, specifically ATM cell switching. In fact, it uses, I would say in a sense, it uses what is called as virtual circuit switching, where virtual circuits are established, but packets or cells of data are sent. So, you can see that it is distinctly different from the primarily circuit switched mode of operation that is used in narrowband ISDN. Okay. So, if you look at if you continue on looking at the difference between these two, NISDN uses predefined channel rates. We have seen that it uses B type channels and D type channels, and there are two basic rate and primary interface rates which are supported, whereas BISDN uses virtual channels without pre-specified rates. So, it is almost like saying you have bandwidth on demand. So, depending on your application, depending on the demand of the application, bandwidth can be allocated. So, it is a bandwidth on demand kind of technology. So, if you look at what exactly broadband ISDN tries to provide for you, as we said earlier, it is an integrated network for data, voice and video, which is similar to that of what ISDN normally does. But it is different from the traditional data and voice networks, because of course, the processing complexity is critical for high data rates. We are looking at a broadband network, which means it also provides much higher data rates compared to the normal other networks. So, and the data networks traditionally have variable delays and due to flow control varying data rates, whereas voice and video, they require fixed bit rate and delay. So, when you are trying to combine both voice, video and data and provide these three services using a single network, then we have to keep in mind that we have these different requirements from these different types of data, and we need to provide for all these different type of data. When you say voice and video requires fixed bit rate and delay, whereas data networks can tolerate variable delays and they could have varying data rates. So, both fixed data rate as well as varying data rate has to be accommodated in a technology which tries to cover both these. So, that is what a broadband ISDN endeavors to do. So, if you look at ATM and try to understand how the ATM technology has been designed to provide these services, we will see that the BISDN traffic typically is carried using asynchronous transfer mode at the physical layer. That is, we talk about ATM cells, ATM technology. Okay. So, if you look at what we mean by this ATM, asynchronous transfer mode, you can kind of try to distinguish between what we mean by ATM, which is asynchronous transfer mode, with synchronous transfer mode or STM. So, what would STM indicate? It would mean that all channels will use some standard multiple of 64 kilobits per second. So, that is a synchronous transfer. ATM on the other hand is more flexible. So, it is asynchronous in that sense, that gives you that flexibility of having different data rates being supported. Again, bandwidth on demand, that is the point that we are looking at. So, STM, which again you can look at it as narrowband ISDN, that is circuit switched, whereas ATM, as we said, is packet switched or cell switched with virtual circuits. And ATM benefits from high speed packet switching and very large scale integration circuits. That is, the way the ATM switches are constructed and the way the cells are processed, all this is done with the help of some very sophisticated VLSI circuits, so that this entire cell processing and switching gets done in hardware. So, you have data coming in terms of cells, and these cells are switched using these switching circuits, which are entirely constructed using some specialized hardware. So, which gives you the advantage of high speed processing. So, you are able to transmit the data, do the switching and make sure that you are able to meet the requirements that you have for timely delivery of data. So, that is what the ATM switches try to do. So, as we said, the ATM basically provides the physical layer for BISDN. However, if you look at the function that ATM performs, it is actually doing the function of a network layer, because as we said, it provides packet switching and handles bursty data. So, if you look at the reference model, the protocol reference model that is typically used on BISDN, it would go like this. So, you can see that there are basically 3 planes of operation that we talk about. We have something called a control plane, a user plane and a management plane. So, you have different functions that will need to be carried out by a BISDN protocol. That is, there will be some management functions to be done, there are some control functions to be done, and there are some user functions that need to be carried out. So, we have 3 different planes that we talk about, and in each plane if you look at the bottom you have a physical layer, then we have what is called as an ATM layer on top of that, then we have something called an ATM adaptation layer, normally it is shortened out to AAL, and then on top of that we have a higher layer protocol. Okay. Now, all these protocols, they exist in all 3 planes, that is, you have a control plane, user plane and the management plane. Okay. So, this is typically the layered architecture that we have for the BISDN protocol reference model. Okay. So, if you look at what these different planes actually are supposed to provide, so user plane is the one which provides for user information transfer. Control plane, if you look at, it takes care of call and connection control. That is, how do you establish a call, how do you establish a connection, control of these parameters, these are handled by the control plane. Then you have the management plane, which is responsible for 2 things. It is responsible for plane management, that is how the whole system functions, and it is also responsible for layer management. Okay. So, when we talk of layer management, what we essentially mean here is the different resources and parameters in the protocol entities, how is it that they need to be managed. So, all these are taken care of by the management plane. So, user plane is meant to provide user information transfer, control plane takes care of call and connection control, and management plane provides both plane management and layer management functions. Okay. So, these are the various functions that need to be handled in the different planes. Okay. So, if you look at now we just saw that there is something called an ATM layer, then we have something called an AAL layer or the ATM adaptation layer. So, the purpose of this adaptation layer which is sitting right above the ATM layer is to divide the message or bit stream that is coming from above into ATM cells, and at the other end it will reconstruct the messages or streams at the receiver. So, the sender side, it is responsible for taking data from the application or from the layer above and convert it into ATM cells, and on the other side it does the reconstruction. Okay. So, this is what is done by the ATM adaptation layer typically. So, now trying to take a look at the ATM cells, the different cells that we have, we said that ATM sends data in terms of cells. So, what exactly is this cell? So, the cell is the basic unit of transfer. Okay. So, it is a fixed length of 53 bytes. Okay. So, this whenever we talk of ATM, we refer to ATM cells. So, these are basically packets of 53 bytes, out of which 48 bytes is data and 5 bytes is the header, a 5 byte header and a 48 byte of data. So, that is the way the ATM cells have been designed. So, you can see that they are pretty small, right, the cells are very small, it is just 53 bytes forms a cell. There is a lot of There has been a lot of deliberation that has taken place before arriving at this particular size of data. The idea of having small cells is it becomes easier for you to do the processing, especially in hardware, and secondly the delays can be reduced, especially when you have small packets standing behind large packets. The moment your packets now are divided into cells, if I have a small packet of 53 bytes and even if I have a larger data that needs to be sent, that would anyway be split up into cells. So, since it is all 53 byte cells, all 53 byte equally sized cells, handling the data, handling different types of data and providing timely delivery becomes easier. So, that is one of the major advantages of going for this kind of a cell based structure. Okay. So, continuing on the ATM cells, we will see that we can see that as I said, the fixed cell size makes the switches much simpler. Okay. So, and per cell processing is normally done in hardware rather than in software. Okay. The per connection processing is still normally done in software. Note that there is a difference between per cell processing and per connection processing. Per connection processing is the process of establishing a call from end to end and then processing and then making sure that once you have established the call, then the data can be transmitted. At the end of it, making sure that you disconnect the call. All this is what we mean by connection processing. So, this per connection processing would still normally be done in software, but per cell processing, that is when each cell comes, looking at its header, identifying what needs to be done with that is normally done in hardware. So, which is why you are able to do it much faster. Okay. So, as I said, the cell size is a compromise. So, small size is selected to minimize the packetization delay for voice transmission, especially when you look at voice or real time data transmission. We are very much concerned with the packetization delay, that is the delay that is taken up in making them into packets and sending them out as packets. Now, larger cell size would be more efficient for data, right, because per packet the header overhead would be less. When you have, see, typically when you have larger cells or larger packets, the amount of overhead that is sent per packet is definitely in an overall sense will definitely be much lesser. When you use small size packets, remember that for every small packet that is sent, there is an overhead. So, there is definitely some kind of a compromise that we are looking at over here. So, the cell size, as we said, is a compromise in the sense that you are definitely trying to minimize the the delay for voice transmission. At the same time, you may have a little bit more of overhead for data, but it is okay because you are trying to accommodate both. So, that is the compromise that we have in terms of the size of the cell. So, if you look at the ATM connections, we just talked about ATM cells and we said there are something called ATM connections, right. So, as I said, ATM is a virtual circuit network or it is a connection oriented network and it uses virtual circuit switching. So, we all know what is meant by virtual circuit switching, that is there is no physical end to end connection established, but virtually we have a connection established from end to end, resources are allocated and then the data is allowed to go through. So, you have some kind of a guarantee in terms of the successful transmission of data. Okay. So, in ATM we have two types of virtual circuits. We have what is called as permanent virtual circuit and then we have switched virtual circuit. So, in permanent virtual circuit what happens is that you have connections and paths that are established through the network when the network itself is established, that is permanently you have certain virtual circuits set up. Right at the time when the network is set up, all these paths are set up. Okay. So, this is what we mean by permanent virtual circuit. On the other hand, we also have what is called as a switched virtual circuit, that is on an as needed basis connection and paths can be established throughout the network. Okay. Now, permanent virtual circuits are suitable when you are looking at some applications where you are looking at dedicated paths that need to be provided. So, this is more like dedicated lines that are provided, whereas switched virtual circuit is used whenever we are having a network which is providing some services and those who need the services use the services as and when they need it. So, this is used on an as needed basis. So, you look at how this circuit switching actually takes place with the help of these virtual circuits shortly. We will take a break and then come back and take a look at this. Welcome back after the break. So, we've just been looking at ATM connections. We said ATM is a virtual circuit switch network, which means it is a connection oriented network. And we said there are two types of virtual circuits, a permanent virtual circuit and a switched virtual circuit. So, PVC and SVC as it is referred to. So, let us look at some more details of this virtual circuit switching mechanism. So, the fact that it is connection oriented eliminates the need for source and destination addresses in the header. Remember, we have 5 bytes of header for every cell, every 48 bytes of data that is sent. So, which means we would definitely like to reduce the amount of overhead that is there in the header. So, the fact that we have a connection oriented mechanism eliminates the need for source and destination addresses in the header, which would be required if you are doing a packet switched approach. So, here because it is a virtual circuit switching approach and it is a connection oriented mechanism, we do not need source and destination addresses in each cell. That is a major advantage. And similarly, there is no need for a sequence number for each sequencing, because again it is a connection oriented approach. So, there is no chance of packets being reordered. Okay, that is, so we do not need any, we do not have problems of reordering. Therefore, no out of order packets, we do not really need the sequence number. So, we are reducing the some of the fields that would normally be there in a packet switched kind of scenario. Okay. Second thing is error control and flow control are only done on an end-to-end basis if needed by the application. So, again the overheads that you would normally have in terms of error control and flow control in a packet switch network are done away with, because we use again a connection oriented approach. Okay. So, these are some of the major design decisions which allow ATM to give you this higher speed of operation. So, if you look at the ATM virtual connections, you will see that it uses two types of virtual circuits. Okay. It refers to what are called as virtual channels, and then you have virtual paths. Okay. There are virtual channels and then we have what are called as virtual paths. Okay. So, if you look at the relationship between the physical link, the virtual path and the virtual channel, it basically goes like this. The physical link contains multiple virtual paths, and the virtual path, each virtual path can contain multiple virtual channels. Now, this virtual channel is the one which actually provides the logical path between the ATM endpoints. That is, between two endpoints, what we have established is a virtual channel, and multiple such virtual channels are put together to form a virtual path, and multiple such virtual paths would be carried in a single physical link. Okay. So, we have this hierarchy of virtual channels that we have here, virtual connections that we have here. There is something called a virtual path, and then we have something called a virtual channel. Okay. So, this picture probably gives it to you a little more clearly. So, you can see that you have a physical transmission path, inside which you will have virtual paths. Inside each of those virtual paths you have virtual channels. Okay. So, this is what we need to understand. So, what is the job of this virtual path and the virtual channel? Again, you can see that both are essentially virtual connections. One is this virtual, but we have a two level virtual connection, the channel connection and the path connection. So, in every cell we will need to identify each of this, whether it is what is the virtual channel and what is the virtual path. So, we talk about a virtual channel identifier and a virtual path identifier. So, what is this virtual channel identifier? So, you will see that this virtual channel identifier is a 16-bit field in the header, 16 bits, okay, in the header. So, what is the purpose of this virtual channel identifier? As I said, it will identify a virtual channel on a link between two ATM switches. So, given that you have 16, it is a 16-bit field, you can have up to 64K different channels that can be carried over a link. Okay, this is the virtual channel identifier. Now, the virtual path again is identified by means of a virtual path identifier. So, this virtual path identifier is either an 8-bit field or a 12-bit field in the header. The reason we have two different 8-bit or 12-bit is because there are two different formats that are supported, which are used in two different purposes. So, either we may have an 8-bit VPI or we would have a 12-bit VPI. So, the purpose of this is to identify a path over which the VCI does not change. Okay, note this. The VPI, the virtual path identifier, it identifies a path over which the VCI does not change, and this is normally used for semi-permanent connections. Okay. So, I will give you an example of what actually happens with both VPs and VCs. So, normally when we talk of the ATM switches, we talk about VC switching and VP switching. That is, whether the switching happens with respect to the virtual channels or whether it happens with respect to the virtual paths. Okay. So, if you look at a typical scenario, this is what it would look like. You will have multiple connections coming in, and at the VC switch, right, this will take care of virtual channel switching. This is sent on a particular path. Then you have a VP switch here where the path switching would take place. That is, the path identifier would be changed, indicating that now it is going on a different virtual path, okay, on a different path as such. And then you have a virtual circuit, this is again a virtual channel switch. So, you would have basically combinations of VC switches and VP switches, and depending on whether it is a VC switch or a VP switch, either the channel will be switched or the path information will be switched. Okay. So, let us take an example and see exactly what we mean by this VP switching and VC switching. Okay. So, let us say for instance, I have these 3 connections coming in. Okay. I have an A, B and C, 3 different cells that are coming in. Now, this A has VPI set to 1, VCI set to 9. Okay. This is VPI 1, VCI equal to 8. This is VPI equal to 2, VCI equal to 7. So, you can see what is happening here. 2 virtual, this is a single virtual path, both these are on the same virtual path, but the virtual channels are different. Okay. So, the virtual path identifier itself is different here, it is 2, whereas it was 1 in these 2 cases, and the VCI obviously is different. So, these 2 are from a single virtual path, this belongs to a different virtual path. In the same virtual path, these 2 belong to 2 different virtual channels. Okay. Now, this goes to a VP switch. At a VP switch, what will happen is the VP will change, but not the VC. Okay. So, you can see what is happening here. So, this packet B or the cell B, when it is switched as VPI equal to 3. So, packet number 1, VPI number 1 is being switched to VPI number 3. But if you look at the VCI, what was 8 here continues to remain as 8 over here. The same thing you can see with respect to packet number A. Okay. So, you see this VPI 1 here becomes VPI 3 here, but the VCI number 9 here and the VCI number 9 here, they remain the same. Okay. And if you look at C for instance, C may not undergo any change in the VPI. So, you could have C and another which is continues to remain at VPI equal to 2. Okay. And so, let us say for instance, now we come to the VC switch, okay, or this is another VC switch. At this VC switch, I could have another packet D coming in from some other VPI, coming in through another virtual path. So, this means it has a different VPI obviously. So, this has a VPI 3 and this fellow has a VPI 2. Okay. So, now let us say both of them have the same VCI value of 6. So, when it goes through a VCI switch, you will see that it is the VCI, the VC that is changed, but the VP remains the same. So, the virtual path, the VPI which was 2 here for C remains at 2 for C, VPI which was 3 for D remains at 3 for D, but the VCI value which was 6 here becomes 5 here, which was 6 here becomes 8 here. Okay. So, it is at the VC switch the VCs are changed. So, VCI from 6 here becomes 8 here, but the VPs are the same, VPI is 3 and the VPI is 3. So, same thing you can see happening with respect to this VC switch as well. Here I am having these 2 packets A and B coming in. So, the VPIs remain the same at 3, whereas the VCs are switched to different values. So, this is what happens in a VC switch and a VP switch. So, if you look at the header functionality, what actually happens in the ATM header, you can see that the header provides for the following functions. It provides for identifying connection, that is we just saw that you will have something called a virtual connection identifier, a channel identifier and a virtual path identifier. All this will be part of the header. So, you will have connection identification. In addition to that, there are 3 other things which are provided by the ATM header: provision for congestion control, cell loss, handling of cell loss and payload type. So, we will just take a look at what this ATM header looks like. As I said, there are 2 different formats for the ATM header. One which is used for a user network interface, that is when the user is connecting to the network, and another is when you use a network node interface, that is inside the network, one from network device to another network device, we use something called NNI. So, UNI format and NNI format, very slight difference between these 2 as we can see over here. If you look at the UNI and NNI formats, in the UNI you first have a field called GFC, which is followed by VPI and then VCI, 8 bits of VCI followed by you have another 8 plus 4 plus 4, 16 bits of VCI, and then there is something called a payload type field, we have a cell loss priority field and there is an error control field. This is called as the header error control field. In the NNI format, almost all these fields remain the same, except that the VPI now, instead of being 8 bits, uses 8 plus this another 4 over here, 12 bits. So, the 4 bits of GFC that you had here, that becomes part of the VPI. So, this is why we said VPI may be either 8 bits, which is in this case, or 12 bits as in this case. Okay. Okay. So, if you look at we try to understand what these different fields basically do for us. The VCI and VPI together identify the virtual connection. So, 24 bits in the UNI format, 28 bits in the NNI format, and a special reserved address indicates unassigned or idle cells which carry no data, but are needed to fill up a cell slot during the transmission. Remember, we have a synchronous transmission that is normally used. Okay. So, the GFC that we have, the generic flow control field that we have, this is used to control the traffic flow at the user to network interface. This is basically to alleviate short term overload. So, we have some kind of a flow control that is introduced at this level. There are two sets of procedures that are used over here. One is uncontrolled transmission, the other is controlled transmission. So, every connection may be subject to flow control or not, that can be decided, and the flow control is from subscriber to network. Okay. The payload type that we looked at, right, the field that you have called the payload type, this basically distinguishes between whether it is user data or network control information. So, 3 bits basically are used for this purpose. Then in addition to that, we have something called a cell loss priority, the CLP bit as it is referred to. This one bit indicates whether this particular cell can be lost, that is, can I afford to drop it in case there is some congestion in the network. The way this is handled, we will need to look at that in detail later, but right now just yes, this is a provision that is provided in the cell header. Then we have a very important field which is the header error control field. Now, this is a CRC check over the header. Remember, this does not include the data. Just for the header part, we have a CRC check to make sure that your header is intact, right. So, it is very important that at the high rates of data transfer that we do, any errors in the header which can cause total damage to the transmission as such are identified immediately. So, we have a header error control field which is a CRC check over the header. So, to summarize what we have looked at so far are basics of the broadband ISDN, and basically we have tried to give you an overview of the ATM technology, the asynchronous transfer mode technology. So, if you look at ATM, we talked about the architecture of ATM, we talked about the fact that it uses virtual circuit switch network, virtual paths and virtual circuits, two different levels at which the virtual circuit switching and virtual channels, the two different levels at which it works, cells as the basic unit and the structure of a cell. So, this is what we have looked at in terms of understanding the basics of ATM today. So, questions to review the content that is covered today. Question number 1, what are the characteristics of BISDN? Question number 2, what kind of switching technique is used in ATM? Question number 3, why does ATM use fixed size cells? Question number 4, what is the size of an ATM cell? Question number 5, what are the fields in the ATM cell header? Thank you.